So today we'll cover the force lesson, and as you can see in this image, this is a simple demonstration why the force is important. You can see this picture is called as the title of this picture is the world's strongest flea, right? And you can see with the simple mechanism of the wheels and the attached rope into a flea. With the jump of the flea, this rotation can be the movement can be identified or introduced to this mechanism. But even with the smallest amount of the tiny bit of the force, it also can be practically applicable in any case. And in today's lesson, we'll discuss about the definitions of the force, especially the Newton laws and the self-balancing forces. We'll talk about different types of forces, and then especially the friction force and the resolving forces for today. If I define the force, it can be defined as a push or pull of an object considered as a force, and it can be a direct force, or you can use, instead of the direct force, you can use indirect force. You can even put a similar object like this near the same object, and you can apply the same force. So which means that the push and pull come from the objects interacting with another as well, right? And in simple definition, it is the push or pull of an object with mass causes it to change its velocity. So that is one thing to remember. Whenever there is a force, there should be a change in velocity. That is for a fact, right? Or and in further further explanation about this force, it is called as external agent capable of changing the body's simple body or rigid body. It is states of rest or motion. And when we talk about the force, right, we should have a method to measure that, right? So definitely there is a uh, magnitude as well as a direction, a specific direction. And when we talk about the direction, we can talk about the vectors, right? And basically the direction towards which the force is applied is known as the direction of the force. For example, you can see using the hand is actually pulling this object, right? This is the direction of the force, and you can see the velocity changing it into its direction, and the simple A means the acceleration. We'll talk into this in a bit. And force has the specific direction, that is, and it is given in this upper arrowhead.
So the down one is the acceleration.
Yes, down one is acceleration.
Okay, sir.
So here is how you can identify whether there is a force is applied or not. There should be a definite change in the speed and change in direction. We can obviously understand there should be a change in direction, but what do you think about change in speed? If you take a fan, let's say we'll take a fan and we'll turn it on to the speed, let's say speed 3. So that fan is rotating over an axis to a certain amount of speed, right? However, if it is turning with the same velocity, if the velocity is not going to change, then we cannot say the speed is not going to change, right? However, if you obstruct the speed, the constant velocity, by just say you are putting a hand into the fan and you are obstructing its velocity. Now the constant velocity is obstructed. If there's a difference in velocity over a time, we can assume that as an acceleration, right? So there should be a change in speed as well. And here are some real life observations you can do. Even for A-level questions, you can think about these things. Force can make a body that is at rest to move. It can stop a moving body or slow it down. And third one is it can accelerate the speed of a moving body. It can also change the direction of a moving body along its shape and size. Okay, change in direction can also be done. And discussing into further, the unit for the force is called as a capital N, the newtons. The SI unit is newtons, and the SI base units you have to learn about when it comes to A levels, because there are several MCQ questions when it comes to. I have seen several questions actually in the MCQ paper. They are asking to describe the base unit, right? So Newton, let's look at the equation first of all. So equation for the force usually is that F is equal to M multiplied by A. Now, up to this point, you already know what is called as the M, right? M is given by the, M is the mass, right? Mass means it is measured in kilograms. The A means the acceleration. It is given by M is minus 2. So if you take it as a base unit, it is the kilograms, M is minus 2. And we don't usually use this one over and over the time. Instead of this base unit, we just call this one as the newtons, capital N. There are other units as well, but they are not in our case. So as I discussed earlier, you can describe force with the magnitude, direction, and there's a third factor as well. The force line of action, which means a point where force is applied and its extension, also known as the line of action. So first one, magnitude, the direction, and the force line of action. Now, if you look at this figure at the right hand side, you can see here we have the magnitude. Let's say this is 10 newtons. Okay, just assume the value 10 newtons. Okay, the direction is given, magnitude is given. What is the line of action then? So this is the force line of action. Why we need a line of action? There's one important part or with that. With the line of action, you can actually change its value as well. For example, instead of this F, I can put it like here, and the original assumed value is 10 newtons to this side, right? So either I can take out that arrow to the other opposite side, and I can say this is minus 10 newton, right? That is the importance of having the line of action, right? So either you can take, either you can counter, okay, you can mention the value as a negative value or positive value, depending it's by just changing the location, changing the original location. Now, since we learned about the Newtons, let's talk about the Newton's three laws. Actually, there are three laws, and the first Newton's law is called as the concept of inertia or momentum, and it is defined as every object continues to be at rest or move with uniform velocity unless otherwise acted upon by a resultant force. Then that can be easily explained. Let's say, for example, let's say this is a book, and this book is located on top of a table, right? And actually, there are two conditions here: at rest or move with uniform velocity. At rest or move with uniform velocity. So the first scenario is for the rest condition, and I will explain for the second condition, move with uniform velocity. For that, I will take an example. Let's say we'll take example a fan, a ceiling fan. Let's say this is the rotation axis. So this is a ceiling fan, and let's say it is in a constant speed. So it is rotating with a constant velocity. Let's say V is equal to 5 ms minus 1, the unit of velocity, 5 meters per second, right? Now, if you consider the first scenario, the book is actually, it is in the rest condition, right? It is not moving. So I can say velocity is equal to 0 ms minus 1, which basically says that object is not moving at all. And here, this is how you can understand the Newton's first law. He just said that every object continues to be at rest. So rest objects are going to stay at the rest position, and the objects moving with the uniform velocity is going to do the same continuously unless otherwise acted upon by a resultant force. So what is this resultant force? Now, if I draw the forces acting on this uh, first figure, so we have the mass is applying, the weight of the object is applied from the center of the gravity to the earth gravity point, and the resultant force, or the reaction force acting from the table on onto the book actually. So these are the two forces applied. However, in this case, these two forces are this resultant, sorry, the reaction force and the weight of the object. I can say the weight of the book is mj, and the reaction force, these two are balancing with each other. So it is actually at the rest position. However, if I am not applying any external forces like this, let's say if I am pushing this book in this direction. So if I am not applying any kind of a resultant force, so objects at the rest are in the rest position. Objects actually with the uniform velocity continues to be in the same manner. So if I'm putting my hand in here, and if I'm obstructing the velocity, then there's a force acting. Okay, that is very simple as that. And as I said earlier, the same Newton's first law is called as the concept of the momentum, right? The momentum is also another term we can learn of. How to get the momentum of any object? You just have to multiply its mass by the velocity. So mass is given by simple m, velocity is given by simple v. So momentum, it is not initially defined as the simple p. Okay, there's no specific term for momentum, but you can just remember that it is just the m multiplied by v. And if I now ask the base unit of this momentum, what it should be? M means the kilograms, v means the ms minus 1, right? And this is also a vector quantity. Vector means it has a magnitude as well as a specific direction. And if you understand this momentum concept, if I ask two questions now, which of the following object has the highest momentum? For example, let's say there's a moving train. Okay, there's a moving train, and let's say there's a simple tennis ball with a small simple tennis ball thrown off by a 5 year student, 5 grade student or something like that. So which which has the highest momentum? Is it the train, moving train, or the ball thrown by a 5 grade student? It should be definitely the moving train, right? Why? Because the in a moving train, the mass of the train is very high, right? It is not in kilograms, it is even in tons. However, the velocity is somewhat low. However, the mass is higher and velocity is lower. However, we can have a higher momentum. And when it comes to a tennis ball, it has a very low mass because the tennis ball has a hollow core. And as well as I think 5 year grade student cannot throw it much of a speed, right? Much of a velocity. So in that case, it has a lower momentum. And learning about the momentum, the the idea is that the higher momentum objects we cannot stop the higher momentum object easily. For example, we cannot stop the moving train like a car, right? And for example, look at let's say for a good example, let's take a bullet, a moving bullet from a gun. The bullet has a it has a lowest mass. However, the velocity is much higher. So we cannot stop a bullet, right? That is why it is piercing through. Because whatever the object has the highest moment, they are very hard to stop. Right. Now we'll discuss about the balanced and the unbalanced forces. Right. For example, okay, in the first figure, you can see a car is actually moving, right? Actually, so uh, yes. So don't think about the the car practically. Just think this one as a figure, okay? Just think this one as a book, just a book or just a wheel or something like that. Don't think it as a car. So let's say in this car, it is moving in a constant speed or a steady velocity. Let's say there are two uh, forces applying in opposite direction with the equal force value 300 newtons. So in this scenario, we consider this one as a balanced force. Why it is balanced? There's no resultant value, right? There's not a single newton that is come into left or right. We cannot say that because it is balanced in this x-axis direction. X-axis direction, it is balanced. So then I can safely say there's no resultant force. However, if you look at the second scenario,
Sir, so that car is not moving.
No, it is moving in a constant speed with a steady velocity, let's say 30 kilometers per hour. So that's why I said if you take this one as consider this one as a car, you might not understand how this 300 Newton comes off. So just assume this one as a book. So book is pulled by 300 Newton, and again from the opposite side it is pulled by 300 Newtons. However, in this case it might be the not moving, or it might be it might be in a steady velocity. It might be moving, or it might be in a steady velocity. So if you cannot understand what I'm saying, I just can draw this one. So let's say this is a book on the table. Two forces applied in opposite direction. Here it is 10 newtons, and here it is also 10 newtons. All right. So this can be only present in a real situation only if the book is at rest position, or if the book is moving in a steady velocity, moving with a steady velocity. Let's assume a value v is equal to 2 meters per second. Right. So these are the two conditions according to the Newton's first law. So just don't worry about this car, how these 300 newtons and 400 newtons are coming on. Just think about anything like this, a book or something. Okay. Okay.
That 300 going behind is the friction, right?
Yes, you can understand. Yes, it is definitely due to the friction. Yes, by the engine, it is by the rear drive or the front drive car is applying a force in the opposite direction, 300 newtons. But due to friction, I mean, in a real situation, this can't be possible, right? Or is it? Actually, it is possible.
Can't. So,
No,
but
no,
if
it is possible.
there's zero force, right?
No. Even though there is no resultant force, you can 300 newtons can be achieved. Let's say this car is a front wheel drive. So in the front tire, it is creating 300 Newton to this side. However, the I think the friction is applied in here, in along this way. If I take it as arrowhead in this way, and it is going to be I mean uh, the friction is also increasing with up to a certain limit with the applied force actually. So otherwise we cannot drive a car, but it is going to drift or I mean burn out in the same position. This can be possible, and with this you can see it is moving in a steady velocity in a straight line. However, in the second case, you can see there are two different values for opposite direction, which make this one as an unbalanced force. And you might wonder what is the resultant force, because in the A-level questions you have to find out the result from force more uh, constantly, right? For the force questions, that is the first thing you have to do. Obviously, it is going to be 400 minus 300, 100 newtons. And as I said earlier, force has to be given with the magnitude as well as the specific direction, right? So you have to say the 100 newtons into the right direction. That is the resultant force. Yes, this side 100 newtons, which means the resultant force is basically means that instead of these two forces, I can just say, I can just apply 100 newtons in the right direction. That is the same thing that these two forces do by do the work by itself. And the third scenario is it is the same thing, an unbalanced force, and you can see the resultant force should be 100 newtons to the left side, right? 300, 200 is pulling in this way. So resultant is 100 into the left. And when it comes to reference books, you can identify, I mean, there are a lot of definitions. However, this is the simple, uh, I mean, the idea you have to take. And now, since you already know about the resultant force, then I can say if no net force, so it is another term for the resultant force. If no net forces or net force acts on a body, it is the same thing denoted by this text. The body's velocity cannot be changed, which means the body cannot accelerate, which means it is basically at the same velocity or it is at the rest position. So as we discussed earlier about the inertia, this law expresses the concept of the inertia momentum. And when it comes to the inertia of a body, it can be described as being its reluctance to start moving or to stop moving once it is started. Actually, this is a good definition you can give for the inertia or the momentum of a body. Reluctant to start moving or to stop moving once it is started. And once you do the in the engineering technology classes, you might learn about the flywheel of the engine, right? So the flywheel is the product of the momentum. The flywheel is actually a product of the momentum, right? Okay. Right. And as I discussed earlier with that example of a moving train and a tennis ball thrown by a 5-year-old, a large mass require a large force to change its speed or its direction by a noticeable amount, right? So the body has a large inertia, thus the mass of a body is a measure of its inertia. So for example, if a model car, very toy car, has a mass of 2 kilograms and a velocity of 2 meters per second, so momentum of the inertia is going to be 4 kilograms meters per second. Now we can talk about the lot of this idea of the inertia. However, uh, we don't need to learn that much of that, right? So it is the same thing I have discussed earlier, given in here, right? You can think about the inertia. For example, let's say you are catching a football, right? And compare it with a less massive tennis ball moving at the same speed. So which one is hard to catch? So usually it is the football, right? Because it has a higher mass. And as I said earlier, when the mass is increasing, the inertia is also increasing, right? Which means it is very hard to move it. So for example, a stationary car, pushing a car is very hard at first because the inertia is much higher. And since you already identified the Newton's first, the law of motion, I think it's Newton's second law. Um, let's go into the next slide. Yes. Look at this question. Use the idea of inertia to explain why some large cars have power assisted brakes. So when the car is getting larger, the inertia is also getting larger, which means you cannot stop it very quickly, which means you have to apply huge power, huge braking power. So for that, we have to apply the power assisted brakes. Think about the trains actually. They have the steel brakes, right? They have to use the friction for each and every wheel to stop the train. So this is the same thing. The inertia is also again the linear momentum, linear inertia, just the same thing we have discussed earlier.
Sir, then for the Newton's first law, there's only one equation, P equals mv.
Yes, P is equal mv. And now actually when it comes to the questions, it is all start with the F is equal to ma. It all start with the Newton's second law. Right. Now in the second law, it is stated that the rate of change of moments. So how do you write down the rate of change of moments? Let's look at the first case. How do you write down the change of moments of an object? Change of moments means, let's say, object is first of all it is at the rest position, and let's say in a second scenario it is moving with a certain velocity. Let's say in the first scenario the velocity is 0. Now after certain time the velocity of this object is 5 ms minus 1. How do you write down the change of moments now? When it comes to a change, it should be last minus the first, right? So the mass is not changed because we are considering the same object. So change of moments can be written down like this, right? mv minus mv. Am I correct? So this is the last moment, m multiplied by v. This is the first moment. So this is the change in moments. However, this is not suitable, right? Like the both terms are given by v, velocity. However, we have an exception. The first
mv
velocity,
minus mu.
yes, mv minus mu. You already know this is right. Then the rate of change means whenever there is a term called rate, which means we have to divide it by the specific time, right? The given time. So basically in this 5 phrases, this is the equation I can write down. So rate of change of moments of an object is proportional to the unbalanced, also known as the resultant force, which acts on the object. When we talk about the proportions, so proportion sign can be written down like this. And for the resultant force, I will take the F here. And to convert this one into equation, you have to multiply this this equation by the constant, by a constant that is applicable for every equation in the known physics and also in the mathematics. We have to multiply it by a constant to remove this proportional sign. So I will multiply this by the constant k and I'll assume this value as 1. So which means it doesn't actually affect the value, right? So f is equal to, then we have f is equal to this value, because k is going to be 1, it doesn't make any difference. So basically f is equal to the same equation. And further, you can take out this v minus u and t to one side, which basically equal to the acceleration, right? So the common term is the mass. So mass multiplied by acceleration, then the f is going to equal to ma, right? F is equal to ma. That is the major equation we are going to use throughout each and every force equation. So I can take out the m, v minus u divided by t. So this is equal to change in velocity, the rate of change of velocity, right? Which is equal to the acceleration. So I can simply say f is equal to ma, right? Or you can say the inertia or anything like that, the linear moment or anything, it doesn't matter. Now in the second term, this is the equation. Right.
So should we write down any notes or?
No, I will share the presentation. Shall we start in after 10 minutes? I think my time's up.
Okay.